Okay, so thank you for joining me, and I hope I'm able to kind of present this stuff and it'll make sense, and then you'll have at least a few extra days to kind of study the material here. All right, and so this material, just to kind of avoid confusion, even though it is technically week 5 Friday, the material is posted in week 6 on CCLE, and you will answer the questions in the I'll write week 5 Friday / week 6 Monday lecture quiz. Okay, so it's the quiz, the viewing quiz for this material is listed under week 6. All right. Okay. So we left off, and I think we ran out of time to review data collection. And so how we collect data actually matters as far as, what kind of tests we can do, what kind of conclusions we can make, and all sorts of stuff like that. Okay. So so here, this is just a silly example that we're going to revisit a few times. And basically, there's two aspects. Is random sampling used, and is random assignment used? And you have a few different kind of combinations of those things, and what kind of conclusions you can make depends on whether random sampling was used, or if you have a representative sample, and or if random assignment is used. Okay, so let's say we have a dentist and they want to know if vitamin C will result in fewer canker sores than someone without vitamin C. Okay, so 500 milligram vitamin C supplement or something, maybe drinking orange juice or something where you get a bunch of vitamin C or something. Okay, and so scenario 1, the dentist convinces all of the dental patients in town with appointments during the first 2 weeks in December to be subjects of a study. Okay, and then he divides them into 2 groups: those who normally take at least 500 milligrams of vitamin C each day, and those who do not. Okay, and then he asks them, how many canker sores do you have in your mouth, and checks dental records and looks at this, and he compares those who take the vitamin C with those who don't.
The Dyson skill, where you can control and monitor your Dyson
I don't know what's going on there. Okay. And he finds that there's a difference in the 2 proportions, right? Where there's a significantly smaller proportion having canker sores of those who take vitamin C. Okay, and so what kind of conclusion can we make? And the answer is, since the patients do not represent a random sample from any population, it is not possible to make any inference about this result holding for a larger population, right? So if we look at this, we looked at patients with appointments in the first 2 weeks in December. That's not a random sample, okay? And so this we cannot generalize to the larger population. Also, as far as the treatment, this is just observational. Who takes vitamin C on their own accord and who does not, okay? So we can't make any kind of cause and effect conclusions. So all we can really say is just that for these patients, those who take vitamin C have fewer canker sores than those who don't, okay? We don't know why, and we don't know if this result would be consistent with another group. All right, so here's another scenario, okay? Here we're still going to take patients with appointments in the first 2 weeks of December. So we're not doing a random sample, but we do use random assignment, okay? We're gonna tell some of them that they have to take vitamin C, and then the other, we tell them to abstain from taking vitamin C, okay? And so, I don't know, is this even possible? Is this ethically possible to tell someone you're not allowed to take vitamin C and stuff like that? Maybe, maybe not. But anyway, we're going to pretend we can do this experiment. And at the end of the experiment, we look at the proportion of those who had canker sores and those who don't. And we'll find, there is a significant difference in the 2 proportions, where those who took the vitamin C have fewer canker sores. All right. And so what can we conclude here? All right. So again, it's not a random sample, so we can't generalize to a larger population. However, because the treatments were randomly assigned, okay, and assuming, other kind of factors are controlled for, or at least randomized, the difference in the proportions can be attributed to the vitamin C, right? Because we randomly said some people are going to take vitamin C and some people are not. And if we truly did a random process, there should be no reason for why one group would experience more or fewer canker sores than the other group, except for the kind of vitamin C difference. And so the conclusion here is we don't know if this result would be consistent with another group, but for this group, we believe we know why the proportions differ, and that's going to be because of the vitamin C. Okay. So continuing to kind of work with this, this time we're going to select a random sample of dental patients in town. So we have to somehow we're able to obtain a random sample of the dental patients in town, and we get them all to participate in the study. And then, and here we don't do random assignment. We just say some take vitamin C on their own accord and some do not. Again, we do our study and we find a difference between the proportions. And now this time, because the patients are a random sample, we can infer that the results observed in this study would be consistent with results from the whole population. And this time the whole population would be all dental patients in the town. Okay. However, because this study was observational, we cannot make any kind of conclusion about cause and effect. There could be some kind of confounding variable. Okay. So, and as far as the general population goes, our population, the whole population, is just dental patients in this town. So we can only generalize because our sample came from the population of dental patients in the town. So we can only generalize to that population, dental patients in the town. But, if you do believe that your town's dental patients are representative of, other like larger cities' dental patients or the larger population of people in general or something like that, then you can kind of try to generalize there. But it's, that those are major assumptions, right? We have to, in statistics, we always have to make some assumptions, and some of those assumptions might be right or wrong. Okay, and so we just have to kind of be aware of what mistakes we might be making with different assumptions. Okay, and then the last one is we're going to have random sampling and random assignment. And if you have both random sampling and random assignment, then you can generalize to your general population because of the random sampling. And because of a random assignment, you can make a cause and effect conclusion. All right. So, so for the population of dental patients in the town, we know that taking vitamin C, those taking vitamin C have fewer canker sores than those who don't. And we believe that the reduction is a consequence of taking the vitamin C, okay? And if the dental patients of this town are representative dental patients in general, we can infer the dental patients who take vitamin C tend to have fewer canker sores than those who don't, okay? So, this fourth scenario where we have both random assignment and random sampling and random assignment is kind of a fantasy scenario. It's almost never going to happen in real life. Okay, so the reality is, having both a random sample and random assignment is almost never possible. Okay, because generally, to do random assignment, to have an experiment, that's going to require patient or participant consent. And, as soon as somebody says, I don't want to participate, the group is no longer going to be a random sample, right? It's no longer. So even if you went through the process of sampling, randomly selecting people, as soon as somebody says, I don't want to participate in the study, it's no longer a random sample, okay? Have any of you already taken Stats 101B? No, maybe. And in your 101B class, did you do an experiment on the island? No, maybe. Okay. Well, in some stats 101B classes, you do an experiment on the island where you have to kind of like select a sample. And part of the structure of that experiment or that simulation is that it's actually really difficult to get a truly random sample. They intentionally made it difficult to get a random sample because that's a lot like real life. It's very difficult to get a random sample. So you kind of get some kind of sample and you're hoping that the sample is kind of representative. But again, you have to ask for consent and not everybody consents. And then, you gather data. And so the whole point of 101B is, designing your experiment. And generally the process of finding participants and gathering data is time consuming and expensive. And so when you design your experiment, you want to design your study in such a way that the conclusions you make, you can maximize the information you get from basically as few observations as necessary, right? You don't want to waste money and waste time gathering data that you don't need. Okay, so anyway, all of that to talk about randomization tests, okay, and bootstrap tests. And so, we covered a bit of statistical inference earlier in our last lecture. And here we're going to be doing some more statistical inference, but we're going to use the computer to simulate or create our sampling distributions for us. Okay, so here's I'm just completely making up this scenario here, but we're going to ask, is the proportion of international students different for statistics majors and applied math majors? Okay, so in my classes, I have a lot of students who are stats majors. I also have a lot of students who are applied math majors. Okay, and I'm just making up these numbers, and we're going to just say we get a random sample of 150 students majoring in statistics, and of those 150 students, we'll say 75 of them are international. Okay, and then we'll also say we have a random sample of 160 students majoring in applied math, and of those students, 64 of them are international students. And so the question is, does this provide evidence that the proportion of international students is different for students majoring in stats and students majoring in applied math? So again, the key here is we're assuming that these are random samples. Okay, so one way we can compare these, there's a few tests we can do. One is we could do a chi-squared test, but you could also do a z proportion test. So I don't know if you guys recall this from your intro stats days, but we're going to say, all right, what is the sample proportion of international students for stats majors? We're going to do 75 divided by 150, and we get a sample proportion of 0.5. Okay, what's the sample proportion of international students for the math majors or applied math majors? So we do 64 divided by 160, and we get a proportion of 0.4. All right, and so the difference between the proportion of international students in stats and the proportion of international students in applied math, that difference is 0.5 minus 0.4. We have a difference of 0.1, a difference of 10 percentage points between the two proportions. And the question is, is that difference of 10% significant or not? Okay, so this is doing a traditional kind of hypothesis test. So this should be review. And so the null hypothesis in our case would be that the two majors, stats majors and applied math majors, have the same proportion of international students, okay? That the proportion of international students is some number. And the only reason why we're getting a difference of 0.5 versus 0.4 is just because of random chance, okay? When you do random samples, sometimes you get too many in one group and not enough in another group. That could explain our difference. So our null hypothesis is that in the population, the proportion of international students and the proportion of international students in math those two proportions are the same or that they have no difference. That would be the null hypothesis. The alternative hypothesis is that the two majors have different proportions of international students, okay? That the proportion of international students in stats and the proportion of international students in math, they're different, and therefore that difference is not equal to 0, okay? And so if the null hypothesis were true, what we would expect is whenever you take two random samples, we expect those sample proportions to be similar and to have a difference something around 0. But what we got in our data was we got a difference of 0.1. We got one proportion is 0.5 and the other proportion is 0.4. So the question is, that difference of 0.1, is that statistically significant? Okay, so in order to answer that, we have to figure out our sampling distribution, and we can figure this out using the central limit theorem. And you might have forgotten this formula, but this would be the formula for the standard error of the sampling distribution. So we say, okay, this difference that we observed, p hat stats minus p hat math, this could be treated as a random variable, and the random variable would come from the normal distribution centered at 0, because if the null hypothesis were true, we would expect these two values to be the same, so they would have a difference of 0, and the standard error would be given by this formula, okay? And p hat is calculated using this. So if we do that, we want to know, okay, what's the p-value? What's the probability of getting our difference of 0.1? I don't know if I'm doing this too quickly, but hopefully this is a little bit of review, maybe from your intro stats days. Okay, maybe. And so our p-value is, what's the probability that two populations with the same proportion of international students, right? So if the null hypothesis were true, the two populations have the same proportion. And the question is, if the world had the proportion of international students in stats and the proportion of international students in math, if they were the same, how often would random samples have a difference of 10%? 10 percentage points, okay? How often would that happen? And that's what we want to know. What's the probability that this would happen? So our p-value is going to be the probability that the difference between the proportion in stats and the proportion in math, how often is that difference going to be greater than 10%? I guess it should be greater than or equal to 10%, okay? And it's the absolute value, because it would be interesting to us if the proportion of international students in stats is greater than the proportion of international students in math. It would also be interesting to us if the opposite were true, if the proportion of international students in math were greater than the proportion of international students in stats. Okay. So the calculation, we do this and we get a z-score of 1.77, basically 1.769. That difference of 0.1, the standard error is 0.056. So we get a difference, a z-score of around 1.77. That corresponds to a tail area of around 3.8%. And when you multiply it by 2, you get a p-value of around 7.68%. Okay, 0.0768. That's going to be the p-value that we get when we do our calculations. And so our conclusion here is that our p-value is 0.0768. If we use an alpha, a significance level of 5%, our p-value ends up larger than alpha, and we are not going to reject the null hypothesis. And so what we say is that the data we have does not provide evidence that the proportion of international students is different for statistics majors and applied math majors, okay? And we're just saying if the proportion were the same, we would expect samples drawn to have the same proportion. We didn't get the same proportion. We got two samples where the proportion proportions were different. One proportion was 40%, the other proportion was 50%. We had a difference of 0.1, okay? And it turns out that you could still get a difference of 0.1, and that's going to happen around 7 to 8% of the time. It's not, super common. It's not a very large probability, but it's not small enough for me to just kind of ignore it. Okay, so therefore we're not going to say that the difference of 0.1 was caused by something other than random chance. It could have been caused by random chance. Okay, it's also possible that the reason why we got a difference of 10% is because the populations do have different proportions. So that's also possible, but we're not ready to say, that's definitely the case either. Okay, so we're not going to reject the null. Okay, it doesn't prove that the null is true either. So in order to use the Z proportion test, that relies on the central limit theorem. You need to have samples that are large enough. Your samples need to be randomly selected, okay? And large enough means you need at least 10 who are yes and 10 who are no, which means, do we have at least 10 international students and 10 domestic students in both samples? And the answer is yes, okay? We had, 75 international, 75 domestic in one. We had 64 international and I guess 96 domestic in the other, okay? So both of those numbers, all of those numbers are over 10. So our condition for sample size is met, okay? But sometimes if these conditions are not met, okay, using a Z proportion test will give you the wrong p-value and you could end up making the wrong conclusion. So in that case, we might need to use a randomization test. Okay, so let's talk about a randomization test. All right, I'm going to pause the recording here because I'm going to play this video, but it's copyright protected, and so if I record it, I'm going to get a copyright strike. So I'm going to go ahead and pause the recording here. Okay, all right. So if you're watching the video, if you didn't attend live, which is going to be most of my students because there's only about 9 students here, that's okay. Let me just give you a brief recap of the video that we just watched. Was it was an episode or a little segment from the Mythbusters TV show, so it's like a decade old now, but they had people participate, 50 people participate from the kind of the local market, and they had them sit in a room alone where they were just kind of being monitored by video cameras for several minutes. And before each participant entered the room, there would be somebody that just says, oh, go ahead and please sit down. And sometimes that person, Carrie, she would either yawn in front of them before they sat down, okay? Or she would not yawn and they would sit down, okay? And so when she yawned in front of them, that would be the seed yawn, and if she did not yawn in front of them, that would be the control case. And the question was, did people who see her yawn, are they more likely to yawn while sitting in that room, okay? And so the Mythbusters team kind of recorded who yawned and who doesn't yawn. And at the end of the study, so the sample of people that participated is not a random selection, right? It's just kind of a convenient sample of who was there. But the treatments of who got a seed yawn or not, that was randomly assigned, okay? The assignment process was not truly random. It was a systematic process, being that every third person was a control, okay? But the order of people who kind of showed up is random, right? So so we can kind of treat this as who ended up in which group as being part of the results of a random process, okay? And so they said there were a total of 50 people, and they kind of gave us the proportions, and they said, 29% in the seed yawn group yawned and 25% in the control group yawned. So in the seed yawn group, there were going to be 34 participants, and of those 10 people yawned. So your proportion of people who yawned in the seed yawn group, so these are the people who saw Carrie yawn before they sat down, 10 out of 34, so that's about a proportion of 29%, 29.4%. Whereas those in the control group, okay, we had 16 people and 4 of them yawned, okay? And so our proportion of people who yawned in the control group is 4 out of 16 or 25%, okay? And they were talking about it, and Mythbusters goes and they say, there's little doubt it seems to be contagious that these two groups, that because this proportion is 29% and this proportion is only 25%, they're saying the increase in how much people yawn when they see somebody else yawn, which is the seed yawn group, right? So these are the people who yawned after seeing Carrie yawn. They're saying this number is higher, 29%, versus in the control group, only 25%. So they're saying, yeah, when you see someone yawn, it increases your chance of yawning, okay? When you see someone else yawn, it increases your chance. And so the narrator in Mythbusters says, there's little doubt it seems to be contagious, okay? But I think we as statisticians know a little bit better, and we can kind of say, well, we can ask, is the difference between 29% and 25%, is that difference statistically significant, okay? Now, we can't do a regular old Z proportion test because our samples are too small, right? In order to do a Z proportion test, you need at least 10 people who went yes and 10 people who went no, okay? And here, as far as this group goes, we have 16 people total, 4 people who basically, yes, they yawned, and 12 people who did not. So this is too small. We need at least 10, okay? So our sample is not going to be big enough to do a Z proportion test. So we're going to have to do something else. And so one of these things that we can do is a randomization test, okay? Oh, here's how we can kind of express this a little bit more mathematically with a little bit of notation, right? So we can say proportion P seed is going to be the probability that someone yawns, given that they were in the seed yawn group, meaning, they saw Carrie yawn in front of them. And the control will be the probability that someone yawns if they were in the control group. They didn't see somebody yawn. Okay, the null hypothesis is that yawning is not contagious, that these two proportions are the same, that there's no difference, right? Because if there's no difference between those in the seed group or those in the control group, we would expect these proportions, the probability of yawning, to just be the same. The alternative hypothesis is that yawning is contagious. That seeing somebody yawn in front of you is going to make it more likely for the person to yawn. So we're going to say the proportion of those who yawn in the seed group is going to be greater than the proportion of those who yawn in the control group. So we're going to say seed yawn, P seed minus P control is going to be greater than 0. This is going to be my alternative hypothesis. And so in our observed data, the difference we saw between the two proportions, this was 29%, this was 25%. So our difference is around 4%. It's technically 4.4%. Okay, we observe a difference of 4.4 percentage points. And the question is this difference of 4.4 percentage points statistically significant? Could it be the result of random chance, or is it evidence that, there actually is a difference between the two groups? All right, so what we're going to do is we are going to ask what kind of values can we get for the difference, probability of yawning in the C group minus probability of yawning in the control group, if the null hypothesis were true, okay? So the null hypothesis says it's not contagious, meaning that the two proportions in the populations are the same, okay? And we're going to just say, if that null hypothesis were true, okay, then whether someone yawns or not is not influenced by whether someone got a seed yawn or not, okay? Right? Just the people who end up yawning, they were going to yawn either way, right? So that means the difference that we observed, that difference of 4 percentage points, 29 versus 25%, could just be the result of randomness, right? The random assignment, okay? And so, yeah, one way to think of it is to just say, in our group of 50 people, 14 of them were, quote, destined to yawn, okay? It didn't matter that Carrie yawned right before they sat down or she didn't yawn right before they sat down. These people were just gonna yawn anyway, okay? And so whether they saw her yawn or not has nothing to do with it. These people were just gonna yawn anyway. And the fact that one group had 29% and the other group had 25% is just a result of just random assignment, right? When we randomly said some people go into this group and some people go into that group, it just so happened that it got split in such a way that one group ended up with 29% yawners and the other group ended up with 25% people who yawned, okay? And so that difference of 4.4 percentage points can be explained with just random assignment. That's the case if the null hypothesis were true, if the null hypothesis were true. And we want to kind of test that out, right? So what we're going to do is we're going to try to calculate a p-value. The p-value would be, all right, what's the probability of getting this difference of 4.4 percentage points if the null hypothesis were true? And again, if it were true, when you take two random samples, you would expect the proportion in one random sample to be equal to the proportion in the other random sample. We didn't get exactly equal proportions. We got proportions that were similar, 29 and 25%, but they're not exactly equal, okay? And so the question is, if we assume that the two populations have the same proportion, what's the probability that just random assignment, okay, this randomizing process could end up producing two samples where the difference is 4.4 percentage points or something more unusual? All right, is this okay? The idea of trying to calculate the p-value. So what we're going to do is we're going to do a randomization test, right? We can't do a z proportion test because their sample sizes are too small. So what we're going to do is we're going to use randomization to simulate the sampling distribution of different outcomes for that p-hat seed versus minus p-hat control. We're going to create a sampling distribution for the different differences if the null hypothesis were true, okay? And the null hypothesis says that the two proportions in the population are equal, or basically they're coming from the same population, and that random assignment is really just the source of variation between the two samples, okay? So what we're going to do is we're going to set up our data, simulate data in such a way where 14 people are destined to yawn, okay? We're going to have 50 people total, 14 of them are destined to yawn, and then we're going to just randomly assign them into groups. We're going to just randomly pick 34 out of the 50 people to go into group A, and we're going to just randomly pick the remaining, put the remaining 16 people into group B, okay? Because that's what we have in the experiment. That's what we ended up with 34 in one group and 16 in the other group, okay? And so here I'm just kind of randomly shuffling the people up into group A, which has 34 people, and group B, which has 16 people, all right? And because we did this process, we know that if we get a different proportion in group A and a different proportion in group B, we know that difference is just the result of randomization, okay? Because we just randomly put some people in group A and some people in group B, okay? And so who ends up yawning and who ends up not yawning in these different groups has nothing to do with anything else other than the randomization process, because we're doing the randomization. So we're just saying, in our group of 50, 14 of them are destined to yawn, and some of them are just randomly going to end up in this group. Some of them are going to randomly end up in this other group. And we'll find the proportion in this and the proportion in this group, take the difference, and we're going to write that down, okay? And we're going to repeat this a whole bunch of times. And so every time we're going to record the difference between the different proportions. And if we do this enough times, we will get a sampling distribution of what kind of proportion differences can we see, right? What kind of proportion differences could result from randomization? Is it possible that by random chance, one group ends up being like 90% yawners and the other percent 0% yawning? maybe it's possible, maybe it's not possible. We're going to see what could happen from random chance. Okay. And we want to know how often do we get a difference of 4 percentage points. So let me just pause here and just make sure that what I'm proposing kind of makes sense. Okay, all right. Hector, thank you for nodding your head. And I hope everyone else is okay. Nobody gave me a thumb. If you got any questions, please ask a question or raise your hand or something. Okay. The randomization test depends on the assumption of exchangeability. Okay, exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely. Okay, so it means just kind of any permutation is exchangeable with another permutation. Okay, and at a practical level, what this means is we can really only apply this concept of exchangeability to experiments where random assignment was used, right? So we could just imagine if we did this, if Mythbusters did the same experiment, but they set up the tent, you know, like an hour later or an hour earlier or something like that, and they had people participate, the order of people lining up could end up being different, right? They might still get 50 people, but the order of you know, the people in the line could end up being different, and so, you know, who's yawning and whatnot could end up, you know, getting assigned to different groups, right? And so basically exchangeability again applies only when random assignment is used. If the patients are assigned treatments randomly, then any arrangement of patients is equally likely, right? We could just imagine another scenario where, you know, you do some experiment and just based on some other random assignment, you know, you end up getting a different kind of combination or permutation of patients or participants ending up in one group or in the other. Okay. If treatments are not assigned randomly, such as in an observational study, then the permutations of groups are not going to be equally likely. And we can't use a randomization test, right? We can't, if we did an observational study, we can't just say, oh, you know, the people who take vitamin C and the people who don't take vitamin C, that could just be a random thing. Okay, it's there's probably like lifestyle decisions that factor into whether someone is taking vitamin C or not, or something like that. Okay, so this is how we're going to set up our experiment. First, I'm going to create a vector of length 50 where I have 14 true values. Okay, and they're arranged in such a way where I have 10 true and 24 false. This will be my first 34 people. And then I've got 4 true and 12 false, and that will be my remaining 16 people. Okay, and so in my control group, or in my treatment group, I put the first 34 patients where I have 10 true and 24 false. And so the proportion true in the first 34 in my treatment group is 29%. Okay, and the control group is the remaining 16. Okay, true, 4 true and 12 false. That goes into the control group. And so the proportion or the mean control there is going to be the proportion true here. It's going to be 4 out of 16. I get a proportion of 25%. And therefore, in the original data, the difference between the two proportions, 29.4% and 25%, that difference is 4.4 percentage points. Okay, so this is my observed difference. All right, and so what I'm going to do is I'm going to shuffle up these 50 people. Okay, so I've got 50 true false values, 14 are true, and the remaining 36 are false. Okay, I'm going to shuffle those up using sample, right? So we're going to do, sorry, this should say sample, but we're going to just shuffle up the vector, and we're going to put some of them in group A and some of them group B. Okay, now every single one will have 14 true and 36 false, but the order of the values will change. Okay, So here I'm going to do one group. So if I do set seed 1 and I sample, okay, this is a random order. The 50 values have been randomized, okay? And we're going to put 34 of them into group A and the remaining 16 into group B, okay? So who ends up in group A and who ends up in group B is just a result of this shuffling process, all right? And if I say, hey, what's the proportion in group A? The proportion in group A happens to be 29.4%. And what's the proportion in group B? The proportion in group B happens to be 25%, okay? And so just from randomly shuffling the values, I end up getting a difference of 4.4 percentage points, okay? So that just happened just by random shuffling, okay? Just one time, all right? Perhaps this was just a coincidence of this one shuffle, okay? So our random assignment process was able to produce this difference of 4.4 percentage points, which is what we observed in our original data. Our random shuffling process was able to do this just kind of by one randomization. All right. So maybe we'll try this again. Here I do set seed 5. Okay, and again, I shuffle up that vector of 50 values. And I'm going to assign the first 34 to group A. The remaining 16 goes to group B. In group A, the proportion is 23.5%, 0.235. And in group B, the proportion is 0.375. Okay, so group B must have been, because we put 16 into group B. So we got 6 people. So out of 14 people, we had a total of 50 people in our group. 14 of them are destined to yawn. 6 of them ended up in group B, which means the remaining 8 out of 34 ends up in group A. So 8 out of 34 is indeed, 0.235. Okay, and so just by random shuffling, we get a difference of around -14, -0.1397. Okay. So this time, the random shuffling process produces a difference of around -14, where group A actually has fewer yawners than group B. Right? Is that okay? This is what we're doing is just we're randomly shuffling and putting some into group A and some into group B. And we're saying, what kind of proportions are we getting? We want to know what kind of differences can we get from just randomization. Okay. And so here I'm going to do this 10,000 times. 10,000 times. Every single time, I'm going to shuffle those 50 values in that vector yawning. And after I shuffle them, I'm going to put the first 34 into group A. And I'm going to put the remaining 16 into group B. I'm going to calculate the proportion in group A and the proportion in group B. I'm going to take the difference between those proportions and store them into this vector differences. Okay. And I do this 10,000 times. And so now we can see what kind of differences do we end up getting. Okay. So the most negative difference I got was a difference of 0.599, so around 60 percentage points. And then the other greatest difference, I got a difference of 0.411, so around 41 percentage points. Okay, the median value is around 4.4 percentage points. Okay, so what we observed was we got a difference of 4.4 percentage points. And the question is, what is the probability that just randomization produces a difference of 4.4 percentage points or something more, right? So our alternative hypothesis is just, what's the probability that we end up getting a difference greater than 0? So we're only interested in seeing if getting differences of 4.4 percentage points or something more positive. So we're going to see, all right, how many of my differences are greater than or equal to the observed differences, right? So I've got 10,000 randomized differences here, 10,000 randomized differences. We're going to say how many of these are greater than or equal to our observed difference of 4.4 percentage points, okay? And it says out of 10,000, around half of them, around 5,070 of them, okay, end up being greater than 4.4 percentage points. So this is my empirical p-value. My empirical p-value ends up being around 0.5. Okay, meaning what this means is that just from randomization, we could end up getting a difference of 4.4 percentage points, right? So Mythbusters on the TV show, they said, oh, 29% versus 25%, that's a difference of 4 percentage points. It's not dramatic, but definitely that means we've confirmed this, this theory that yawning is contagious, because we got 29%, which is greater than 25%. 29 is, we have, after they saw the person yawn, the probability that they yawn is 29%. We said that's bigger than 25%. Therefore, when they see someone yawn, it increases their probability of yawning by 4 percentage points. And they say that that means yawning is contagious. But it turns out that even if the null hypothesis were true, okay, meaning that yawning actually isn't contagious, right? Even if the null hypothesis were true, even if yawning is not contagious, if you're going to just have a total of 14 people yawn, and you just split them up into two groups, one where you have 34 people and the other where you have 16 people, you're going to get a difference of 4 percentage points around half the time. You're going to get a difference of 4 percentage points or something greater. That's going to happen 50% of the time. So you could have just gotten lucky with the coin flip, basically. Right. It could have just been just a coincidence. Okay. And it's not even that weird of a coincidence that this happened, right? It happens 50% of the time. So what we're going to say is the data we have doesn't actually provide evidence or provide a reason to believe that getting a seed yawn makes a person more likely to yawn. Okay. It doesn't prove, it doesn't mean that yawning is not contagious. It just says this is not the evidence you're looking for, right? If you're trying to prove that yawning is contagious, this is not the evidence you're looking for. You got a difference of 29 versus 25%. That difference is not big enough to really convince anyone, okay? So we can't conclusively say that yawning is not contagious, but we're just saying our data is not providing the evidence that it is contagious, okay? And so, you know, in reality, it's possible that the seed yawn does increase the probability of yawn, but maybe we didn't collect enough data, or maybe just, you know, in the experiment, we happen to get fewer people yawning or something. So that could be possible, but as it stands, our p-value is 50%, which is, you know, much greater than, say, an alpha of 5% or something. Okay. If the alternative hypothesis were something like, does seeing someone yawn have any effect, right? A positive or negative effect on a person yawning, right? Like it would be interesting if you see someone yawn and that reminds you and go, oh man, I got to be careful not to yawn. And so you avoid yawning. Okay. So it's possible that seeing someone else yawn actually reduces your chance of yawning or something like that. Okay. And if that were the case, you would be interested in both of the outcomes. Does it increase or decrease your chance of yawning? Okay. And so in this case, we would look at the absolute value of the difference. So we'd be interested in positive differences or negative differences. Okay. And we ask, okay, well, what proportion of these differences, absolute values of the differences, are greater than or equal to the observed difference? And it turns out all 10,000 out of 10,000 of them ended up with a difference greater than or equal to 0.044. Okay, so we're getting a p-value of 1. A p-value of 1, is that even possible? Okay, and yeah, a p-value of 1 actually could happen, or in our case, is the result, because if you look at the data, right? So we had 14 yawn and 50 people total, and here we're going to put 36. And I'm sorry, 34 in group A and 16 in group B. Okay. So right now we have 10 out of 34 versus So 10 out of 34 is like 29%, right? 0.294 versus 4 out of 16, which is 0.25. Okay, so that's a difference of 0.44. The difference is this, right? On the other hand, let's say we move it around. So we have 11 out of 34 in group A yawn. So 11 out of 34 is 0.323, 3235, okay? And then that means in the other group, we can only have 3 out of 16, right? 3 out of 16, because we have a total of 14 people. So 3 out of 16 would be 0.1875. Okay. So the difference between 11 out of 34 minus 3 out of 16, that difference is 0.136. All right, so so you get anything else, you get a difference that's bigger than 4%. Okay, what if we went the other way? We could have 9 out of 34. 9 out of 34 is 0.2647. And the other group would have then 5 out of 16. 5 out of 16 is 0.3125. Okay, and so what's the difference between there? 9 out of 34 minus 5 out of 16. That's a difference of negative 0.0477. Okay. So we got a difference of 0.044. It is literally impossible to get a difference that is any smaller than this. Okay. Because if you flipped it around the other way, either you get 11 and 3 or 9 and 5, because we have a total of 14 people. And so when you assign these 14 people who are going to yawn into either group A or group B, the proportion differences that you're going to get, the smallest one you can possibly get is 0.044. The next smallest would be a difference of negative 0.047. Okay. And so if you take the absolute value, this is the smallest possible difference that we get. So it's actually not even possible to get a smaller difference than 4.4 percentage points. Okay. You could get a difference of 4.7 percentage points, but in the opposite direction and things like that. So that's what we're seeing. It's not possible to get anything. So we end up getting a p-value of 1. Okay, meaning every single randomization results in a difference equal to or greater than 4.4 percentage points. So we would definitely not reject the null hypothesis in that case. You know, I forgot. Let me go ahead and give you your view quiz answers. I think this is my first one, right? First view quiz answer for today is the letter D. D as in dog. D as in dog is our first view quiz answer for today. Okay, so that was the randomization test. Okay, now I'm going to introduce Bootstrap. Okay, Bootstrap is very similar to the randomization test, except we apply it to different situations. Okay, so again, kind of taking a step back, the sampling distribution is going to be the distribution of all possible values of a sample statistic from all possible random samples drawn from the population, right? And what we're trying to do is by studying the sampling distribution, we get a sense of what kind of values we can get for the sample statistic. And then using that, we can estimate a p-value. How often will we get the sample statistic that we observed in our data, right? The central limit theorem says that the sampling distribution of a mean, of the sample mean, comes from a normal distribution. And the mean is going to be equal to the population mean, and the standard error is going to be equal to sigma divided by the square root of n. And one key idea of the central limit theorem is that no matter what the actual population looks like, it's going to follow this as long as your sample is large enough. Okay. Now, sampling distributions exist for other statistics, not necessarily the sample mean, but the sampling distribution of other statistics like the standard deviation or something else will not be governed by the central limit theorem, okay? And they're not going to follow the normal distribution, right? So the sampling distribution of the standard deviation is only going to be positive. It's not going to look normal, okay? So what we can do now, which is what Bootstrap is all about, is that we can simulate a sampling distribution, okay? But we just have to do this is we have to make assumptions about the population. We're going to make assumptions about the population. And so the first kind of cases we're going to do parametric bootstrap, okay? So for statistics other than the mean, we can rely on our mathematical knowledge of the probability distribution. But even if we don't remember what distribution to use, we can always kind of simulate the sampling distribution. And to do that, we just have to make assumptions about the population, right? So we can either make assumptions about the population shape, the population's mean or standard deviation, or what values could appear in the population. And once you've established your assumptions about the population, we just simulate the sampling distribution by just repeatedly drawing samples, calculating some statistic, and recording it. So here, let's take a look at parametric bootstrap. All right, so parametric bootstrap works, or is called this because it's going to make parametric assumptions about the population, right? The term bootstrap comes from the phrase, pull yourself up by your bootstraps. Sometimes that's something like, maybe we associate that with like boomers talking to the younger generation about like, oh, just work harder and pull yourself up by your bootstraps or something. And that phrase, the origins of that phrase is debated, but one that always kind of made me chuckle was that there was a story of some folk hero that was walking along, got himself stuck in a swamp, and the way he got himself out of the swamp is he reached down, grabbed his bootstraps, and pulled himself out of the swamp, which of course is a ridiculous thing to think about, but anyway, the idea of bootstrap here is that we are going to try to get information about the sampling distribution without kind of outside help. Okay, we're not going to try to gather more data or something like that. Okay, so when we do parametric bootstrap, we are going to assume that the population follows a very specific parametric distribution. Okay, we often use statistics from our observed sample to help us specify this distribution, right? So maybe we're going to assume that the population has this shape with this mean, this standard deviation. And what mean should we use? Maybe we'll use the mean of our current sample that we have. Okay, so once we do that, we establish what our population looks like. And then we're going to draw random values from this specified population. And from that, we're going to calculate the statistic that we're looking for. We're going to record this and do this over and over, and then we can perform statistical inference. All right, so let's do a let's do an example, right? All right, so let's say we have the SAT exam. Okay, so the SAT exam, some of you guys might have taken it, some of you may not have, but if you look at the verbal side, okay, it's supposed to have a mean of 500 and it's supposed to have a standard deviation of 100. Okay, and but they're also capped so that the maximum is 800 and the minimum is 200, and scores are always in increments of 10. So you can get a score of 640, but it's not possible to get a score of 638. Okay, and so in reality, it's the scores are not actually normally distributed because the students who take the SAT exam are not representative of the general population. But here we're going to just kind of assume scores are normally distributed with a mean of 500 and standard deviation 100. And we're going to take random samples of 15 students. And the question is, what's the sampling distribution of the sample variance S squared? Do you guys remember this from like stats 100B? What's the sampling distribution of the sample variance? Okay, well, let's take a look, right? So here I'm going to simulate our sample. We're going to start off by using R's ability to generate random normal values. And I'm going to say, give me 15 random normal values from a population where the mean is 500 and the standard deviation is 100, okay? But to make them SAT scores, what we have to do is we have to round them to the nearest 10th place, okay? So we're going to say round it to the -1's place, which is going to be the nearest 10th. And if we get any values over 800, replace it with 800. Otherwise, keep the sample value. If we get any values less than 200, replace it with 200, okay? Otherwise, keep the sample values, right? And if we do that, here's one random sample of 15 values. We get a score of 440, 520, 420, 660, 530, 420, 550, 570, so on and so forth. And we say, what is the sample variance of my sample? I get a variance of 10,120.95. Okay. And we can imagine repeating this over and over and over again. Okay. So I'm going to just write a for loop where I do this 10,000 times. Okay. So I'm going to create a vector of sample variances. And we're going to do this 10,000 times. Every single time, we're going to do the same thing. We're going to draw 15 values from the normal distribution. We're going to round them to the nearest 10th place. If any value is over 800, we replace it with 800. If any value is less than 200, we replace it with 200. Okay. Otherwise, we just keep the original sample value. And then we calculate the variance of our sample, and we're going to record it in sample variances. Okay. And so we get, all sorts of values for the sample variances. And this is what the distribution looks like. Okay, the distribution looks like this, has this shape. Okay, so again, the question was, what theoretic distribution can be used to model the sample variance of the sample variance of a sample of random normal variables? The answer is the chi-squared distribution, right? So if you have, and you might not have remembered this, okay? But maybe it was covered in stats 100B, okay? And the idea is if you drew n values from a normal distribution with a mean of mu and variance sigma squared, and S squared is the sample variance, then the result is that you're going to have a chi-squared distribution with n-1 degrees of freedom. So in our case, we drew 15 values. So we're going to have chi-squared distribution with 14 degrees of freedom, but it's also scaled up by this quantity n-1 over sigma squared. Okay, and so I can overlay that. I can overlay the theoretic distribution on top of the, the theoretic chi-squared distribution on top of our values after I scale them. Okay, and indeed we see there's close alignment between our simulation, right? What we did is we simulated these sampling values. We simulated the sampling distribution by sampling a whole bunch of different samples and calculating the sample variances. Okay, and so we can see there's very good alignment between the two. Okay, but so here's the thing is you might not remember all of these relationships. Okay, so if you didn't remember that it was a chi-square distribution, or exactly like what is you might be like, oh yeah, it's supposed to be chi-square distribution, but you might not have remembered that you need to do this scaling, right? You have to take your variances and multiply by n-1 divided by sigma squared, and then that will follow a chi-square distribution. You might not remember that. So what are you supposed to do? Okay, well, again, even if you don't remember this theoretic relationship, you can always just kind of estimate it by using parametric bootstrap, right? Parametric bootstrap gets around this by simulating the sampling distribution directly, right? So here's a question. Let's say you have a sample of 15 SAT scores, right? and the sample variance is 20,000. And you go, and so now the question is it reasonable to believe that this sample is a random sample drawn from this population? Or if you get a sample variance of 20,000, is that an indicator that it's coming from a different population, right? Maybe it's not a random sample, okay? Maybe it's more to get a sample variance of 20,000. Does this mean it's not really a random sample? You're getting something else, okay? And so we would test this null hypothesis, right? That my standard deviation is 100 versus it's coming from a population where the standard deviation is greater than 100, right? And so we want to say, okay, how often did my sample variances end up greater than 20,000? Okay, because most of the time we're getting sample variances around 10,000, a little bit lower, a little bit higher. How often do you get sample variances greater than 20,000? Okay, now we could try to have figured this out using the theoretic distribution, but here we've created the sampling distribution by just resampling using parametric bootstrap. And we can say, okay, well, how often out of 10,000 times, how many samples ended up with variances over 20,000? Okay, so we're going to say, all right, here I've got all of my sample variances. How many of those are greater than 20,000? And what's the proportion there? Okay, it says, well, it happened 1.2% of the time. So out of 10,000, it happened 120 times. 120 times out of 10,000 happens 1.2% of the time. Okay. So if you have a sample of 15 SAT scores where the sample variance is 20,000, you can either say, you know, I must have been one of those lucky 120 samples out of 10,000. I could have been one of the lucky 1.2%. Or you can say, you know what, I don't think I was the lucky 1.2%. It's not impossible, but it's a pretty low value. So we're going to say this, you know, estimated p-value, this empirical p-value is low enough for me to reject the null hypothesis. And so what we're going to do is we're going to conclude that my sample of scores is not a random sample from a population where the mean is 500 and standard deviation is 100. Is that okay? Does that make sense as far as using the parametric bootstrap to answer questions? Okay, let me go ahead and give you your second view quiz answer. Second view quiz answer is A. A as an apple. A as an apple is the second view quiz answer. Okay. All right, so here's another example. Okay, and again, these are the answering these questions is actually kind of hard to do in real life. Okay, especially because we're dealing with not normal distribution scores truly, but SAT scores. SAT scores where we've artificially capped the maximum value to be 800 and the minimum value to be 200, and they're rounded to the nearest tens place. So it's technically not really the normal distribution. And so I don't know if a theoretic distribution actually exists for some of these answers, right? Okay. Here's another example, right? Let's pretend you have a classroom, a group of say 25 students, and we're going to assume that this is a random sample of 25 students. This is probably a bad assumption because most schools don't put students randomly. They kind of group students together, right? And so what would be the sampling distribution for the highest score in the class, right? So if you have a group of 25 random students and you say, who scored the highest on the SAT verbal? Okay, what would be the distribution there? Okay, so what's the and so if you have a random classroom of 25 students, what's the probability that the highest score in that classroom is going to be 750 or higher? Okay, so what kind of distribution do you have there, right? So there technically is a theoretic distribution that can be used to find the extreme value, like the maximum, okay? And that's known as the Gumbel distribution. But I suspect that many of you are not familiar with it or would know how to use it, okay? So we can take just, in my opinion, a much easier approach than trying to remember or figure out what theoretic distribution to use, okay? And so I'm a big fan of kind of, the bootstrap in this way, right? So here we're going to, again, we're going to assume that we know what the population looks like, and we're going to use the computer's ability to generate random samples. So we're going to just say, all right, we're going to simulate random values from the normal distribution. We're going to take 25 of them, okay, because now we're saying we're going to have a classroom of 25 students who've taken the SAT. That comes from a population where the mean is 500 and standard deviation is 100. We round off to the nearest tens. Again, we max out the values at 800, minimum value at 200, okay? And then what we're going to do is we're going to take the largest value in our sample. We're going to take the maximum in our sample, and we're going to store that in my vector of highest scores. Okay, we're going to do this 10,000 times, right? So what kind of values do we get? Okay, we got maxes of 800, the median is 690, the minimum is 540, okay? And so if you look at this, this is the resulting distribution. This actually doesn't follow any theoretic distribution. The Gumbel distribution actually wouldn't work here because the SAT has a maximum of 800, right? So truly, there's probably, if we didn't artificially have this max of 800, we would probably get values up higher, but it's capped at 800, so we're not going to get any values greater than 800. Okay, so this is what the resulting histogram looks like. Okay, and so this is the distribution of, what's the highest score in a classroom of 25 students, right? So if you have 25 students, in some classrooms, the highest score is 800. In some classrooms, the highest score of 25 students is 690 or 700. And in some classrooms, the highest score out of 25 students is 600, okay? Things like that, okay? So this is what we want to know, right? So the question is, what's the probability that the highest score in the class is 750, right? Or higher. So we say, okay, well, what proportion or percentage is 750 or higher? So we say, all right, highest score greater than 750, greater than or equal to 750. This will be a logical true false vector. And what's the mean, meaning what proportion is true? 16%, okay? So if you have a sample of 25 random students, there's around a 16% probability that the highest score of those 25 students is going to be 750 or higher. Okay. So, I think these are kind of neat questions to be asking. And if you were given this question, right? If you were given this question and you didn't have the computer, like this would be a lot harder to answer, right? If you were asked to try to figure this out, theoretically, this would be, I wouldn't even know how to approach it just because we're dealing with SAT scores which are capped at 800, okay? So it's, so the distribution is, a lot harder there, okay? So, what if we had a sample of 50 students instead of 25? Sample of 50 students instead of 25, okay? Well, all we have to do, we run the same simulation, except this time we're taking 50 students from the normal distribution, okay? We do everything else, and we say, okay, what proportion of classrooms of 50 students have a high score greater than or equal to 75, okay? And here we get, close to 30%, right? So if you're taking a bigger sample, what's the probability that the highest score is over 75? 750? It gets even higher, which makes sense, right? If you have, with 25 students, what's the probability that your max score is over 750? That's around 16%. If you double that and you have 50 students now, what's the probability that your highest score is over 750? Okay, that goes up to around 30%. Okay. So, here's just some, a silly example, right? A high school, they have 200 students in its senior graduating class. And then the school administration is patting themselves on the back, right? They're saying, hey, look at this. We had 200 students in our class, and out of those, we have 10 students who scored over 700 on the SAT verbal, right? So over 700 on the SAT verbal, that's considered a good score, I think, right? And so so maybe the school administration is saying, yeah, look at us, we're doing awesome because we've got 10 students who scored over 700 on the SAT verbal. Okay, so is this something that the school should be proud of, or is this like an ordinary accomplishment? What do you guys think? Okay, 200 students in the graduating class, 10 of them scored over 700. Okay, so does this sample provide evidence that the student body is something other than a random sample, right? Is this something, is this like something remarkable? 10 students over 700 in a class of 200? Or is this like something remarkable, right? That's not just a random sample. Okay, so how do we answer something like this, right? So what we have to do now is we're going to take a random sample of 200 scores, and we're going to get the 10th highest score. Okay, we're going to ask for the 10th highest score, and we're going to ask, if you have a random class of 200 and you take the 10th highest score, what's the probability that that 10th highest score is over 700? Does that kind of make sense? That's how we're going to try to answer this question. We're going to say, if I take a random sample, if we do have a random sample of 200 students, and we're going to just look at the 10th highest score, and if that's over 700, you know, what are we going to do? Okay, so again, we do the same thing. Our norm, we turn everything into SAT scores. We're going to look at the 10th highest, right? So this one requires us to kind of sort our sample. We're going to sort them from greatest to least in decreasing order. We're going to take the 10th value. We're going to store that into a vector called 10th highest. Okay, so we take the 10th highest score, and we ask, how often do we get, is the 10th highest over 700 if you have 200 people, right? And so we get an empirical p-value of around 3.5%. 3.5%, okay? So the simulation shows that if you do have a class of 200, yeah, you know, it's actually pretty, it's not common for 10 students to score 700 or higher, okay? That only happens around 3.5% of the time, okay? So the school can say, hey, good job, you guys. You know, as far as classes of 200 go, you're in the top 3.5%, right? Because this, something like this only happens around 3.5% of the time, right? So the school can be proud of this, okay? But it doesn't necessarily mean the school is responsible for this, right? It could have just been a coincidence where, you know, you got a very studious class or something like that. So, you know, the school can be proud, but they can't necessarily claim responsibility for their students' success. Maybe they can. I mean, maybe they are responsible, but who knows, right? So we are able to ask, you know, how often does something like this happen? And we get the answer, and it happens around 3.5% of the time. So not a huge number, right? So this is something fairly impressive, but also, you know, as far as why, who knows why, okay? So the key here with parametric bootstrap is you have to be comfortable with the idea of saying the population looks like some way, right? So here we've been doing SAT scores. So we've been saying the population is supposed to follow a normal distribution with a mean of 500 and standard deviation 100, okay? Which is probably okay when we're talking about the normal SAT scores. But if we're talking about other distributions, it's hard to know, okay? And so if you are comfortable with stating that the population follows a particular parametric distribution, you can use the parametric bootstrap to simulate the sampling distribution. And then once you have your sampling distribution, you can kind of perform any kind of hypothesis test or get p-values or things like that, okay? But you have to be comfortable saying that the population follows a particular parametric distribution. You have to say the population is normal, or the population is uniform, or the population is chi-squared, or the population is whatever, you know, t distribution, Weibel's, you know, whatever theoretic distribution you have to be comfortable making that claim and saying that this is the values that we're going to have. the other kind of bootstrap we can do is the non-parametric bootstrap, okay? So the non-parametric bootstrap, this is probably when somebody talks about doing bootstrap on a sample of data, when they just use bootstrap without qualifying it and saying parametric bootstrap, if they're just saying bootstrap, they probably are referring to non-parametric bootstrap. Non-parametric bootstrap is called this because we do not make any parametric assumptions about the population. Okay, we're not gonna say the population is normal, or we're not gonna say the population is, you know, t distribution or exponential or something. We do have to make a different assumption, and this is another major assumption, but it's not a parametric one. Okay, when you do non-parametric bootstrap, the assumption here is that your sample has been randomly drawn from the population. And because it's randomly drawn from the population, we can assume that it's representative of the population. Does that feel like a reasonable assumption? Okay, and if you feel comfortable saying that my sample is representative of the population, then you can do non-parametric bootstrap. And if your sample is randomly drawn from the population, you know, you don't really have any reason not to believe that it's you don't have reason to believe that it's not representative, right? If it's a random sample, okay? But if it's not a random sample, maybe you should be worried, okay? So the way the non-parametric bootstrap is going to work is we say, okay, here is, right, you got up here is the big population. We don't have access to it. Instead, you have a sample, okay? And what we're going to do is we're going to take the sample that we've observed and we say, hey, this is like a mini version of the population. This is a mini version of the population. So what we're going to do is we're going to just take it and I'm going to clone my sample like 1,000,000 times, okay? Technically an infinite number of times. And then now I have the population, right? So we're going to say if I have a sample, what I'm going to do is I'm going to take the sample, I'm going to clone it a whole bunch of times, and now I've got this big thing that looks kind of like my population, right? So it's kind of like, I don't know if you guys have played around on Photoshop, but like you can take a patch of grass and you can like clone it, and then you can kind of fill out a whole field with grass, right? And it's kind of that idea that you have a small sample, small portion, and we're going to say, hey, this kind of should look like my population. So what I'm going to do is I'm going to just kind of copy and paste it a whole bunch of times. And now I've got this big thing, and that's going to be my stand-in for the population. Okay. You don't, on a mechanical level, we don't actually take it and manually clone it and duplicate the data. What we do is we take our sample and we sample with replacement. Sampling with replacement is the equivalent of taking your sample and making infinite duplicates of it. Okay. And and then so now that we're going to sample with replacement, which is basically the same as infinitely duplicating my sample, that's going to be my stand-in for the population. Then I can produce a sampling distribution, and then we can make conclusions. What do you guys think of that? Does that make sense for the non-parametric bootstrap, what's happening there? All right, okay. So that's what we're going to do, okay? So we've covered kind of three things. We've had the randomization test, parametric bootstrap, and non-parametric bootstrap. So these are kind of the situations for when you would use this, right? If you have data that you obtained via random sampling, you can use non-parametric bootstrap. If you have data obtained via random sampling and you're willing to make parametric assumptions about the population, you're willing to say the population has this shape, right? The population has a normal shape. The population has an exponential shape. If you're willing to do that, then you can do parametric bootstrap, okay? If your sample is not random, but you have data from an experiment where you used random assignment, then you can do randomization tests, okay? So if your data comes from an experiment where there is random assignment, then you do a randomization test, okay? All right, and so in all of these cases, we're going to create a sampling distribution by simulating many instances of a sample, okay, where the source of variation is just random chance, either random sampling or random assignment. We're going to simulate that using the computer. Okay, so this problem comes from the textbook Ziefler, and I'll provide a link to this textbook on CCLE. Okay, and you should have access. You might have to connect to the school's VPN to get access, but this textbook, this problem comes from the textbook. Okay, and so this was a study performed by the U.S. Census Bureau. And they were looking at the immigrant population, specifically Latin America and Mexico, because that's where the largest source of immigrants to the United States come from. It says the average age of an immigrant is approximately 40 years old, but also there are many children who come and enroll in U.S. schools upon arrival. And then the educational achievement of these children will not only affect their own economic prospects, but also those of their families, communities, and the nation as a whole. All right. And so we had these researchers, Stamps and Bowen. They studied the educational achievement of Latino immigrants by examining a random sample of from the 2000 census. Okay, so this study is now 20 years old. Okay, it's now 20 years old. But the result is provided in this CSV file, latinoeducation.csv. I'll also post this on CCLE. And so one question that's emerged in the research is there a link between where the immigrants originated and their subsequent educational achievement? Okay, specifically, the question is there a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries, right? So, so we have, immigrants from Mexico. We also have immigrants from other Latin American countries, whether, that be, Nicaragua, Costa Rica, Honduras, or even from South America, Latin American countries, Venezuela, Colombia, and things like that. And the question is there a difference in educational achievement? They're kind of tracking the educational achievement of some of these immigrants, okay? And so the data here, they're looking at 150 Latino, or maybe we should say Latinx immigrants living in Los Angeles, okay? And this is the kind of the data dictionary that we're looking at, okay? Now, they have measured some educational achievement level, okay? And this is a scale of educational achievement ranging from 1 to 100, in which higher values indicate higher levels of educational achievement. Now, I tried to look up what exactly these numbers represent, and it's not revealed to us. So, like, if somebody graduates high school and ends their educational journey there, I don't know what number that is, okay? And if the student goes on to college and graduates with, let's say, a 2-year degree, I don't know what number that is, or a 4-year degree, I don't know what number that is, or maybe they go on and get a PhD. I have no idea what any of those numbers are going to be. All we know is that 1 means their achievement education is less, and 100 means their education achievement is a lot higher. But in reality, I was trying to look up what exactly the numbers translate to, but I couldn't find that information. So we just have to kind of trust that the numbers are accurate, okay? And I wish I had better answers here. And this is, I should just kind of mention, some of you might be interested in like going online and finding data sets on your own and doing your own little data analysis projects. And I think that's a great idea. One thing I caution you though is make sure that the data has some reasonable source for the information. You don't want to just pull up random data that somebody made up. And also try to see if they have something like this, right? If they have a variable, say achievement, or a variable just, I think there's like a music data set on from Spotify or something, and they have numbers like danceability or like valence or something. And they assign some kind of number. Yeah, you want to ask yourself, what does it mean for the number to be 100? What does it mean for the number to be 50? What does it mean for the number to be 3? And hopefully you have a way to kind of explain that, okay? And unfortunately, I don't have a way to explain this, what these numbers actually mean. All we know is higher means more and lower means less, but I wish there were reference points. They provided reference points, like a 4-year bachelor's degree is a 70. I don't know, okay? And a high school diploma is like a 55. I have no idea. I wish there was some number, but they don't provide that, okay? There's other other variables. The immigration year in which the immigrant arrived in the United States, okay? So if somebody arrived in the year 1981, their number would be 81, okay? 81.5, that would be like June 1981, okay? Immigrant age at the time of immigration, and then we have, is this immigrant or individual fluent in English, 0 or 1, and is the immigrant from Mexico, okay? 0 for people who are not from Mexico, 1 for people who are from Mexico. And really, we're just going to be looking at the interplay. Is there a difference between immigrants who came from Mexico and their subsequent educational achievements? So we're really just going to be looking at this variable and this variable, okay? And again, this is a observational study, so it has nothing, we cannot draw any kind of cause and effect conclusion, and it's an observational study, and so random assignment is not used, okay? We cannot just randomly assign and say, oh, you are going to be, in this group, you are, these are not treatments. These are not things that we can apply to people. This is someone's identity, right? They either came from Mexico. These people came from Mexico. These people who have zeros here did not come from Mexico. They came from some other Latin American country, okay? And again, I don't know what these mean, okay? 63.1, 63.7, 63.1, 67.6. I don't actually know what those numbers mean, okay? But we're gonna just see, is there a relationship between this column for whether the person came from Mexico or not, and their educational achievement level, okay? And so here, just kind of doing some quick exploratory analysis, I'm going to do a summary, and we're going to say, okay, what's the mean education achievement level for people not from Mexico? The mean is 64.5. People from Mexico, the mean is 58.6. What about the standard deviation? And we had a total of 150 people, 34 and 116 came from Mexico, 34 came from other Latin American countries. So this is actually a much smaller sample, okay? And so the difference between 64.5 and 58.6, if we keep more decimal values, is around 5.9, okay? And so we see the difference in the means is around 5.9 between the two groups. And the question is, is that difference of 5.9, is that significant or not? Okay, and here's a kind of a box plot. And, for those who came from Mexico, this is the distribution. For those who did not come from Mexico, this is the distribution. And we're just asking, is there, is the difference between here and here, is that significant? This shows the median, technically not the mean, but, it's kind of similar, 64.5, 58.6. I think this is around 58.6. This might be a little bit higher than 64.5 for the mean. Okay. If we did a plot, here I have overlying kind of kernel density plots. And so Mexico is in light blue. And then in red, we have people not from Mexico, other Latin American countries. And the question is, is the center different for these two groups, right? And it's kind of hard to fully analyze, right? It's hard to say, maybe this is significant, maybe not. Okay, and again, this is what we want to know, right? So our traditional t-test, we would do the two means are equal, or that the difference between the two means is 0. And then the alternative is that the two means are not equal to 0. Okay, and if you do a t-test, you get a p-value just under 5%. You get a p-value of around 0.04597. Okay, and we could probably do a t-test, if we assume our data is a random sample, because our samples are large enough that we could justify the usage of the central limit theorem and do a t-test. Okay, so this would be your traditional approach. But what we can also do is we can apply non-parametric bootstrap. Okay, non-parametric bootstrap. So here we are assuming that our sample is representative of the population. Okay, and what that means is that we can take our sample, make infinite duplicates of it, and have that as a stand-in for our population. Okay, and so what we're going to do is we're going to build up our sampling distribution kind of by using randomization. Okay, and we're going to keep our quantity that we're going to investigate is the difference for X bar and X bar for people from Mexico and X bar for people from other Latin American countries. Okay. The null hypothesis states that the mean education achievement level are equal for both groups. And if we assume that variances are equal, then the null hypothesis effectively states that values for both groups are basically coming from the same population, that it doesn't make sense to kind of separate off people from Mexico from people from other Latin American countries, because we can kind of treat, as far as educational achievement, we can kind of treat them all as, coming from the same population. Okay, and not, and we don't necessarily have to segment one group from another. Okay, that's what would be the case if the null hypothesis were true. Okay, and again, this is only in regards to this one variable, education achievement. Of course, we don't want to just say, oh, everybody's coming from the same population or same group, with regards to other aspects or things like that. Okay. So this is how the non-parametric bootstrap would look. Okay. If the null hypothesis were true, we're basically saying the achievement scores for Mexican immigrants come from the same population as achievement scores for other Latin American immigrants. Okay, and so what we're going to say is, under the parametric bootstrap, our 150 scores that we have in our sample is representative of the entire population. So what we're going to do is we're going to draw two random samples, one of size 116, because we have 116 immigrants from Mexico, and we have 34 immigrants not from Mexico. And we're going to draw two samples from all 150, okay? Because again, under the null hypothesis, basically we're saying the scores for the Mexican immigrants and the scores for the other Latin American immigrants are coming from the same population. If the null hypothesis were true, if the null hypothesis were true, the scores for this group and the scores for this group are coming from the same population, okay? And then, so we're going to say, okay, here I have 116 random values for scores. And what's the mean for these 116? Here's 34 random values. What's the mean of these things? And what's the difference that we get, okay? What we observed back here was that the difference in our data was -5.9. And the question is, well, how often do we get a difference of 5.9? Okay, how often do we get a difference of 5.9? And so, this is what we have, okay? I'm going to keep track. We're going to do this 10,000 times. We're going to keep track of our differences. And we're going to sample 116 values with replacement from the entire column of achievement scores, okay? So Latino $achieve is all 150 scores, okay? Some of them correspond to immigrants from Mexico, and some correspond to immigrants from other Latin American countries, But here we're going to take all 150 values. We're going to just treat them as kind of one population, and we're going to draw the values, okay? And we're going to just say, hey, 116 of them go into group A, okay? And then we're going to take 34 values, and we're going to put 34 values drawn from that group with replacement into group B. And this is what we would get if the null hypothesis were true. And we're going to take the mean of group A, subtract off the mean of group B, and record that difference, okay? And we're going to do this 10,000 times. So that would be the distribution of differences, okay? All right, and so what we want to know is we want to know how often our random differences that we've generated here, how often are our random differences as large as or greater than the difference we observed in our samples data. Remember, the difference we observed in our samples data was 5.9, negative 5.9. How often do we get something greater than negative 5.9? Okay. Now, our observed difference is negative, so the absolute values of differences, okay, because we're interested in positive and negative ones, are always going to be greater than the negative one. So this, you don't just do the absolute value of the difference is greater than the observed differences. This is going to be 100% because our observed difference is negative. So we're going to say the absolute value of our vector of differences, how often is that greater than, you know, the absolute value of negative 5.9, okay? And so we get an estimated p-value of around 0.0465, okay? So this tells us that even when we draw random samples from the same population, sometimes we get, you know, two groups where the difference between means is 5.9 points, right? And that could happen by random chance alone. And that happens just under 5% of the time, okay? So what conclusion would we make, whether to reject the null or not reject the null, is going to depend on the significance level that we're using. If we're using 5%, we would reject it because it's just under 5%. If we're using something like 3%, 2%, 1%, we would not reject because our p-value is greater than those values. Okay, and the p-value we get here, 0.0465, is very much in line with the p-value we got when we did a two-sample t-test, right? When we did a two-sample t-test, the p-value we get is around 0.046. And here, when we did random sampling, we pretty much get the same p-value, 0.046, okay? All right, let me go ahead and give you your very last view quiz answer. Very last view quiz answer is E, okay? Let me just do also a couple more slides here. And then I put in, if we have time, package boot. We clearly don't have time for package boot, okay? But let me just do just a couple more slides here on the parametric bootstrap. So we could also use parametric bootstrap on this for this thing, okay? But we have to make the assumption about what shape the population comes from, okay? So here again, if we assume the variances are equal, then the null hypothesis says that values for both groups come from the same population. So we want to know, you know, what's the probability of observing our data or something more unusual if the null hypothesis were true, meaning how often do two randomly drawn samples have a difference of 5.9 if both samples come from the same population? All right, and so again, this time with parametric bootstrap, we're going to have to make a big assumption about the shape of the population. And in this case, we're going to say the population is normally distributed. Maybe this is a bad assumption, okay? But that's the major assumption we're going to do, all right? What value should we use for the mean and the standard deviation of our normal distribution, okay? Here, we're going to use the overall mean and the overall standard deviation from our data, okay? So we're going to say, what is the mean of that entire column of 150 values? We're going to put all these scores for the immigrants from Mexico and the immigrants from other Latin American countries. We're going to put them all into one group because, again, if the null hypothesis were true, it's just one big population. Then if the null hypothesis were true, it doesn't make sense to separate out immigrants from Mexico from other countries because they're coming from the same population. That's what the null hypothesis is saying, okay? As far as education achievement levels. So we're just going to say, what's the overall mean? What's the overall standard deviation? Okay. And then for the parametric bootstrap, we're going to say, okay, let's draw 116 values from the normal distribution using the overall mean and overall standard deviation. That's group A. Let's take 34 values from the normal distribution using the overall mean and the overall standard deviation. That's group B. What's the mean of group A? What's the mean of group B? Take the difference and then store those. Okay, and so we can do that. We get 10,000 different differences, and we say, okay, out of those 10,000 different differences, how often do we get a difference greater than 5.9? Okay, and we get 0.0466. Okay, so almost the exact same value back here, right? We got 0.0465. Here we get 0.0466. Again, this is just the result of random chance. So again, consistently, we're getting pretty much the same p-value, just something just under 5%. And you know, what conclusion do we make from there is going to depend on what significance level we're using. Okay. Was our assumption of saying that the population follows a normal distribution, is that a good assumption? Well, you look at the histogram of achievement scores. I don't know. It doesn't quite look normal. If you do a QQ plot, I don't know if it's normal, but maybe it's big enough. Maybe our sample is big enough that we can just kind of use the sampling distribution t-test and assume the central limit theorem and stuff like that. Okay. So again, the key idea here with randomization tests and bootstrap tests is that we're using the computer to simulate the sampling distribution if the null hypothesis were true, right? So everything is, what would the world look like? What kind of data could we get if the null hypothesis were true? And if our simulated sampling distribution produces whatever we got, our observed test statistic, if it produces that value frequently, we can say, oh, you know, the statistic we have, this difference of 5.9, that could just be part of the random process, right? We got a difference of 4.4 percentage points. That could just be a part of the random process. We would not reject the null hypothesis, okay? On the other hand, if you say, this is what the sampling distribution would look like if the null hypothesis were true, and it's not able to produce this difference, right? You have a difference of like 20, and every single time you do a random simulation, you get a difference of like 12 or something smaller, and you've never gotten a difference of 20, then you say, you know what? The only way I can really explain this difference of 20 is because my null hypothesis is wrong. My sampling distribution looks like something else. It doesn't look like this. The sampling distribution doesn't look like this because this sampling distribution was never able to produce this difference of 20. So my sampling distribution doesn't look like this, which means my null hypothesis is wrong. Okay, we don't have time. We don't have time for package boot. Some of you might be interested in package boot, so you can take a look at this, but you don't have to. Okay, I will not test you. I will not put package boot on the final exam, and so we will end here. Thank you to those of you who are here watching the video right now, or not the video, came to class live and gave me the thumbs up and whatnot. This is technically our last lecture, and so I appreciate you guys being here. I do have a favor to ask you. I hope you've enjoyed the course. I hope you enjoyed the course. I do have a favor to ask you, and that is to fill out your course evaluation. The questions that matter the most are the two last ones. Yeah, I think you rate them on a 1 to 9 scale. The two last questions are, you know, what's your overall rating of the instructor and what's your overall rating of the course? If you're willing to give me, you know, whatever the highest score you're willing to give me there, that's much appreciated there. Okay. They do make a difference. Okay. And then, you know, any comments you have about, you know, what you liked or didn't like about the course, I do read every single comment we get. I forgot. Let me give you your last view quiz answer for today. Last view quiz answer is E as an elephant. E as an elephant. And again, the view quiz for this lecture is in week 6 on CCLE. I know it's week 5 Friday, but the view quiz is on week 6 on CCLE, and that's just to kind of prevent confusion from people answering the wrong view quiz in the wrong spot. So please don't do that. Okay. I will post a document kind of explaining what you can kind of expect to see on the final exam. So the final exam, so we have no class on Monday. we did the lecture now, and we will have the final exam on Wednesday. Okay, and I'll post a document up this weekend about what you can expect to see on the final exam. Okay, and I'll also post up the last homework assignment, which covers this stuff. And so you can expect to see that sometime, I would say tonight. Okay, thank you, everybody. It's been a pleasure, and good luck as you study, and we will see you on Wednesday. It is a synchronous final exam. Everybody will need to attend live on Wednesday. We will see you then. All right, thank you, and have a good rest of your day. Have a good weekend.